Great. So thanks everyone for joining us today. My name is Misty Bentz, as Margaret said. I'm an associate professor at Georgia State University, and I'm the PI of ERS program 1364, which is nuclear dynamics of a nearby Seyfert with NIRSpec integral field spectroscopy. And before I get started, I just want to take a moment to recognize my co-investigators, who are all very important to the success of this program. So that's Merida Batiste at Emory, Chris Onken at Australia National University, Carolyn Roberts at the University of Iowa, and Monica Valuri at University of Michigan, and Eugene Basilev at Cambridge. So just to give some context for our program, it's good to remember that one of the unexpected and surprising results from the launch of the Hubble Space Telescope was the discovery that basically every massive galaxy seems to host a supermassive black hole in its nucleus. And this was not something that was anticipated before HST was launched. So not only is the discovery of supermassive black holes being quite common, a surprising thing, but also it's quite surprising that we've learned that black holes and galaxies seem to know something about each other. So by using direct black hole mass measurements, in which you can constrain the gravitational influence of the black hole on stars or gas, some sort of luminous tracer particles, we've learned that supermassive black holes that are more massive tend to live in more massive galaxies, and supermassive black holes that are less massive tend to live in less massive galaxies. And so this seems to suggest that there is a coevolution between galaxy growth and evolution and black hole growth and evolution. So direct black hole mass measurements were really important for this particular discovery, but they continue to be important for our understanding of exactly how this coevolution works, what sorts of feedback processes are unleashed from the black hole to affect the galaxy growth, and what sorts of feeding processes are happening in the galaxy to grow the black hole. And not just observationally, but direct black hole mass measurements are really important for providing observational constraints for cosmological hydrodynamic simulations, in which we try to put all the physics that we think we know into a box and run time forward and see if we can grow galaxies that look like the galaxies we observe in the universe today. So both computationally and observationally, direct black hole mass measurements are really one of the keys that we use to try to help us understand galaxy evolution. So direct black hole mass measurements come in sort of two flavors. The first is dynamical modeling. This can be of stars or gas, where you're looking for sort of the unresolved bulk motions of stars or gas as a function of position deep within the center of the galaxy, where you can trace out the gravitational influence of the black hole on those test particles. And this type of direct black hole mass measurement has in the past mostly been applied to quiescent galaxies, and that's just because those tend to be the most common galaxies available to us in the nearby universe, and to mostly early type galaxies. And that's simply because early type galaxies tend to have less messy stuff going on inside. They have less dust, less gas, less ongoing star formation, and so that makes them easier targets for the dynamical modeling. But in the case of dynamical modeling, the black hole mass that you derive depends linearly on the distance that you assume to the galaxy, because you have to convert the angular scales that you see on the sky into physical scales. And not only that, you're really reliant on the spatial resolution that you can achieve with your instruments in order to try to map out the kinematics spatially as a function of position in the galaxy nucleus. And so that means that these techniques are really not applicable beyond a distance of about 100 megaparsecs, because you just can't achieve the spatial resolution that's necessary. Nevertheless, dynamical modeling has given us a sample of approximately 100 supermassive black hole masses, and those masses form the basis for the really well-used host galaxy black hole mass scaling relationships, like the M sigma relationship, or the relationship between the black hole mass and the bulge luminosity. Now, on the other hand, we do have information about black holes outside of the local universe, and those tend to come from results that are tied to reverberation mapping. So reverberation mapping looks at photoionized gas within the center of an active galaxy and measured light echoes within different regions of the photoionized gas. And so it's using time resolution instead of spatial resolution in order to set constraints on physical distances in the galaxy. So reverberation mapping is only applicable to active galaxies. And within sort of the relatively nearby universe, it's mostly the late type galaxies that are active at this point in the universe's history. And so most of the galaxies in the reverberation sample tend to be late type galaxies. And in this case, since we're not relying on spatial resolution, the black hole mass doesn't depend at all on the distance, not for the black hole mass that you obtain in the end. And also, it's not a limitation for the galaxies that you can apply this technique to. And so people are beginning to apply reverberation mapping at redshifts 2, 3, and 4 without significant problems. So reverberation mapping gives us the basis for black hole masses in quasars at a variety of redshifts, including those quasars that we find out at redshift 7, where we're trying to understand how black hole masses have gotten so large in such a short amount of time in the universe's history. But so far, we haven't really been able to test and make sure that the techniques that we're using to get black hole masses at cosmological distances are really on the same mass scale as the black hole masses that we get for nearby galaxies from dynamical modeling. And that's because the requirements for the techniques that you see here means that there's really very little overlap in the samples of galaxies where you can try to apply both techniques in the same galaxies to constrain the same black hole masses. And so as you can see in the plot here, there's sort of 2.5 galaxies where we have published measurements of black hole masses from both reverberation mapping and stellar dynamical modeling and gas dynamical modeling. So NGC 4151, the masses all seem to agree fairly well as far as we can tell at this point. But for NGC 3227, the reverberation masses are consistently giving a black hole mass that's about a half a dex lower than what we're getting from dynamical modeling constraints. And then NGC 4395 here, which is a dwarf Seyfert galaxy with no bulge in the center so that we can't actually carry out the stellar dynamical modeling, has reverberation masses for the black hole, but the gas dynamical constraint there is so broad that the apparent overlap between them doesn't really show that there's much consistency between the models there because the constraints are just so weak. So at the moment, we have a sample of sort of 2 galaxies where we can try to compare the masses that we're getting from different techniques in the same galaxies. In one case, they agree, and in the other case, they don't really agree. And so something that our team has been working on is adding additional galaxies to the sample, really looking for any possible active galaxies where we can carry out reverberation mapping and dynamical modeling to compare the masses that we get from the techniques, but also revisiting some of these measurements and just looking to see if there's any way that we can improve them. And in particular for NGC 4151, which is the focus of our ERS program, we've been working to improve the reverberation masses and the stellar dynamical mass. So JWST plays a part in this because part of our exploration of the stellar dynamical modeling constraint on the black hole mass for NGC 4151 comes from a comparison of what we can get from space versus what we can get from the ground. So for space, we're going to be using the NIRSpec IFU with the high resolution grading, so it's a G235H grading, and the F170LP filter. So that will constrain us to a wavelength range of about 1.66 to 3.17 microns, within which we will see several well-known and often used stellar absorption features that we can use to constrain the kinematics of the stars in the nucleus of this galaxy. And the resolving power of the spectrograph ranges from about 2200 on the blue end to about 4400 on the red end of this wavelength range, and varies as a function of wavelength across it. The field of view that we'll be covering is the innermost 3x3 arc seconds of the galaxy, and that is broken up into 30 slices because NIRSpec is an image slicing IFU, and each of those slices has a width of about 0.1 arc seconds. We're employing a 4-point dither pattern so that we can subsample the PSF at a level of 0.025 arc seconds so that we can really try to constrain our spatial characteristics as best as possible. So for NGC 4151, which is one of the most nearby active galaxies at about 13 megaparsecs, Our best estimate so far put the black hole mass at about 3.6 times 10 to the 7 solar masses. With NIRSpec, we'll have 2 hours on source in which we will try to obtain fairly high signal-to-noise ratio spectra as a function of position within those innermost 3 by 3 arc seconds of the galaxy. And so for the CO absorption band heads, which are around 2.3 to 2.5 microns and have often been used for stellar dynamical modeling in the past, we'll have a signal-to-noise of about 60 in the continuum per resolution element with those 2 hours on source. There's also the possibility that we may observe OH absorption between 2.8 and 3.0 microns, and that would be pushing to the redder end of the spectrograph where the resolving power is a bit higher, but the throughput of the spectrograph is a little bit lower at these redder wavelengths, and so we'll have a slightly decreased signal-to-noise, still 40 per resolution element in the continuum, and that's still within the realm of high enough signal-to-noise that we should be able to accurately characterize the stellar absorption profiles and carry out the stellar dynamical modeling. But we don't know if we'll see those lines because we haven't been able to observe those wavelengths yet because they're not visible from the ground. So in addition to our 2 hours on our primary target, MGC 4151, we're also going to obtain 4 velocity template star spectra as well. And so these are giant, lake-type giant stars spanning spectral classes from K0 to about M4.5. They're all fairly bright at 10th magnitude in the K band, which means that they really require quite short exposure time, about 2 minutes per object, and will easily get signal-to-noise greater than 100 per resolution element in the continuum for each of these objects. But with all of the overheads included, this program is going to take 8.5 hours total, and a lot of that is really just the time that it takes to slew between targets. And so these short observations of the template stars, while absolutely necessary for our program, are really eating up a lot of that program time. So what are we hoping to find with this program? Well, one of the main things we're going to be looking at is how well can you do with stellar kinematic measurements from the ground versus from space. So the JWST program will give us the space-based side of this. We're going to have a moderate spectral resolutions, an average of about 2,700 for the spectra we expect to get for NGC 4151. It has very low backgrounds in space because we're not looking through our warm atmosphere. And then the PSF, by definition, is going to be diffraction limited because, again, we're not looking through our atmosphere. We're also currently working on redoing the analysis of ground-based IFU observations of NGC 4151 with Gemini NIRS, with the AO system employed for that. And so that's going to have, that has a higher spectral resolution in those data, and that's simply because you can build bigger instruments on the ground than you can fit in a rocket and launch off into space, and so you're able to sort of optimize all aspects of the instrumentation on the ground. But of course, observing from the ground in the near infrared is not optimal because the sky is quite bright and a large source of noise. And even with AO, the PSF is only partially corrected. So you have a diffraction limited core in the center, but about half of the light from the central AGN in this object is contained within a seeing halo around that is uncorrected. And so you can see that each of these techniques has something going for them, but they also have some potential drawbacks. And so we're really going to carefully test and see how well you can do in space, and if you actually are able to improve on the black hole masses we get from dynamical modeling, even with a little bit of degradation to the spectral resolution. In addition, we have several other deliverables we'll be providing to the community. In particular, we'll be able to quite accurately characterize the PSF of the NIRSpec IFU. So we'll have our 4 template stars, which are each point sources in not crowded environments. So they'll provide nice characterizations of the PSF. And we can also use the AGN in the center of the galaxy as another test of the PSF as well. We'll be providing 4 template spectra of late-type giant stars, and I expect that these will be quite useful to the community because it means that not all of these other programs are going to have to invest these large overheads to get these short exposures of these necessary template spectra. We're also going to be looking quite carefully at how well you can spatially and spectrally separate a really bright unresolved source that's superimposed on a faint extended source like you have with an AGN embedded in a host galaxy, but also like you find in many other galactic and extragalactic types of situations as well. And so that should provide some useful information for what other programs can expect to get from their science if they're using the IFU. In addition, I touched on this, we're going to be very carefully comparing how well we can characterize stellar absorption profiles, especially the higher order moments of those profiles, using spectra from NIRSpec compared to what you get with higher resolving power from the ground. And then in the case of NGC 4151 itself, which is a very well-studied and quite famous galaxy, we're going to be providing several higher order data products, including kinematic maps of both the stars and the gas, intensity maps of the gas emission, and we'll be able to observe some new wavelengths that have not been observed previously from the ground, and so that should provide new species that haven't been explored before in the nucleus of this galaxy. And finally, we will actually be carrying out stellar dynamical modeling of the stellar kinematics in the center of NGC 4151, and so we'll provide the model for an additional late-type active galaxy, which is in a region of parameter space that has really not been well studied using stellar dynamical modeling so far. So I think I will end there and ask if there are any questions. Thank you.
Well, I have a question. So I'm just imagining how you're going to pull this all together. So you're getting these template spectra of these giants, which I'm assuming you're hoping are within the types of stars that are going to be circulating around the black hole. And then I'm just trying to imagine how you're going to take those to do the job. Are you going to like first take your data and then with your characterized PSF remove the AGN and then just investigate through numbers of point sources you might see around, or are things more blended and so you're having to do like a dynamical model, add the stars in some mixture, and then fit the data?
That's right. It's much more blended, so we won't be able to resolve individual stars in the nucleus of this galaxy. It's just too far away. And so the template spectra provide example spectra of late-type giant stars. So giant stars and especially late-type are the ones that should be dominating the SED of the galaxy at these near-infrared wavelengths. And so what we can do is we can actually look at what different combinations of those template spectra are necessary in order to mimic the stellar absorption features that we see in the galaxy itself. And so you add them together in different combinations and you blur them to determine what the line of sight velocity distribution of a whole group of unresolved stars are that are providing that particular absorption signature that you're seeing. So once you've characterized the line of sight velocity distribution at a variety of positions within the nucleus of this galaxy, then you can put together a library of potential stellar orbits that might be there in the center of the galaxy and see what combinations of those orbits are necessary in order to give you the observed kinematics of the stars that we've constrained by spectroscopy. And so you're really comparing the models to the observations in order to determine how everything's moving around and then how much gravitational motion should be from the stars themselves, and therefore how much is left over that must be attributed to the invisible black hole.
Wow, pretty cool. You talk about the CO and the OH absorption. Could you go back to that slide where you talk about those two absorption lines? So these are the absorption lines you're expecting from these types of stars. Is that correct?
That's correct.
And how deep? I'm just trying to think of contrast with all the light from the stars and stuff.
Sure, yeah. So these are absorption features in the atmospheres of the giant stars that should be contributing the bulk of the light in the center of the galaxy. And in fact, in this little cartoon diagram I showed on the slide before, You see the spectrum of each 2D spaxel at the bottom of that. What they're actually showing you there, those absorption features are CO bandheads, and they're approximately the strength that we have seen in NGC 4151 and a few other active galaxies with ground-based IFU. And so they should be actually quite strong features, and therefore they're easy to see. One thing that's difficult is when you try to explore very close to the AGN in the centers of these galaxies, you have a really bright point source that's diluting the light from the underlying stellar population below it. And so when I mentioned that we were going to be looking at how well we can spatially and spectrally separate those two things, one of those is, how close into the AGN can we probe spatially and still accurately characterize these absorption line features that we're seeing in the spectra that come from the stars and not from the AGN itself.
I see. Okay, very good. Well, I know that there are a number of programs just like yours that are interested in PSF, if you will, subtraction from the IFU. Mm-hmm. So this work, I think, is also going to be very important for pushing forward a number of programs that are going to be happening and are already scheduled to happen. So thanks for being on the bleeding edge of all this.
We're happy to be the guinea pigs.